In this video, we're going to summarize the conclusions that came out of the buffer or not, that is the question lab. So we started that lab by saying that a buffer is a solution that resists changes in pH when you add both an acid and a base to it. And we learned through looking at which solutions did have very small changes in pH that a buffer contains a weak acid or base and its conjugate. So it's always a weak acid-base conjugate pair. That's why conjugate acid and bases are so important to be able to identify. And you can make a buffer really one of two ways. You can add a weak acid or base and a salt of its conjugate in the same amount. So it would be equal amounts of that weak acid and a salt of its base. Or you can take a weak acid or base and add a strong acid base, basically getting yourself to the half equivalence point. So you can add a weak acid or base and half as much strong base or acid. Either of these two things will get you to the conditions of the half equivalence point. And it doesn't have to be exactly equal, it needs to be close to equal. So we're trying to get to this spot here on the titration curve where HA and A minus are equal. So it's really just that it's a titration, but it's a specific spot on the titration curve. So if you think about what we've already been learning about titration curves, there's really nothing new. If we write the Ka value for a weak acid and its conjugate base, and we think about the equation as HA breaks down into H3O plus and A minus, this is the Ka expression that we've been writing all the time. If you just rearrange that to solve for the hydronium concentration, the hydronium concentration is equal to Ka times HA over A minus, the ratio of the acid and its conjugate base. So if we are at the half equivalence point exactly, like if we have exactly equal amounts of weak acid and its conjugate base, then HA and A minus concentrations are the same, and the hydronium concentration is equal to the Ka value. Or you might say the pH of the solution is equal to the pKa, which is just the negative log of the Ka value. We actually talked about this when we talked about titration curves, and we talked about the half equivalence point of a titration curve. Really, a buffer is just a solution that exists like somewhere in this range here on the titration curve where the pH doesn't change a whole lot. So first we're going to be able to identify, is something going to be a buffer or not? So it says, which of the following solutions would make a buffer? And we're going to assume that we have equal moles of each component in this case. So if we had equal moles of Kf and Hf, when we're putting Kf in, K plus ion is basically a spectator ion. It's always soluble. So we're essentially putting in F minus and HF. HF is a weak acid, and F minus is its conjugate base. So yes, this one would make a buffer. KBr and HBr, that would not make a buffer because HBr is a strong acid, and you've got to have a weak acid-base pair. The next one, where it says sodium carbonate and sodium hydrogen carbonate. And again, sodium is always going to be a spectator ion, so we're really putting in the carbonate ion and the hydrogen carbonate ion HCO3 minus. Those two are an acid-base pair. They're a weak acid-base pair because they differ by the presence and absence of a single hydrogen. So yes, that would make a buffer if we had equal amounts or close to equal amounts of those two ions. Then it says write equations that show how the buffer would respond to adding a base or adding an acid. So we're going to take the first example. If we add a base to a solution that has F minus and HF, then the HF is what's going to react with the base. And it's going to make water, and it's going to make a little of F minus. If an acid was added to that same buffer, we're adding H plus, then it's the F minus part of the buffer that's going to neutralize the acid, making HF. So the reason the buffer works is because whether you add an acid or a base to it, there's something there to neutralize it. We have both a weak acid and a weak base, so it'll neutralize both acids and bases. We could do the same thing for the second one we identified to be a buffer above, the second system. If we add a base to the carbonate buffer, then the acid part would react with it. We would have the HCO3 minus interacting with the base to make water and carbonate ion. If we added an acid, the carbonate ion would react with the acid and it would make HCO3 minus. So when you have a buffer, you have both an acid and a base to interact. No matter what you add to it, it will keep the pH about the same. The last conclusion from our discussion in that lab, how could you increase the buffer capacity of a buffer? Buffer capacity means how much acid and base it can handle before it does get to a significant change in pH. So the best way to do that is to increase the concentration of the acid and the concentration of the base. The higher concentration you have of each of the chemicals, the longer it's going to resist changes in pH. The more acid and base you can add to it before the pH really starts to change significantly. And so on this graph, you can see kind of what we're saying with the equations on the previous slide. If you start with a buffer that has pretty relatively equal concentrations of acid and conjugate base, if you add acid to that buffer, the conjugate base is going to neutralize it and will increase the amount of weak acid that is present. If you add a base to the buffer, the HA part of the buffer is going to react with it, reducing the amount of HA present, and you'll have a little bit more conjugate base. But because they're both there, in both cases, it's still a buffer until you completely run out of one half or the other. So that is how buffers work.